Don't forget to subscribe and ring that bell.
Welcome back as we continue the journey down the 2021 free response question section of the AP Calculus AB exam. We already did free response question number 1, and we'll be tackling free response question number 2 today. And I love, that's 4 loves for the 4 hearts, that we get to use a graphing calculator for this section. All right, let us begin. Number 2 states a particle, P, is moving along the x-axis. The velocity of particle P at time t is given by V sub P of t is sine of t raised to the 1.5. We don't see this notation that often. All this means is the velocity of my P particle, because chances are there's going to be another particle. We normally see velocity like this. But when I have 2 equations and 2 particles, I put particle P here. And oh, look at this. We are eventually going to have a second particle Q, but I'm getting ahead of myself. But just don't get confused with that notation, okay? Let me get rid of that. And we left off right here. So we have our velocity equation for particle P for time between 0 and pi inclusive. At time t equals 0, the particle is at position x equals 5. All right. A second particle, Q, also moves along the x-axis. The velocity of particle Q at time t is given by V sub qt is t minus 1.8 times 1.25 raised to the t for all time between 0 and pi inclusive. At time equals 0, the particle Q is at position x equals 10. That was a lot to read. Find the positions of particles P and Q at time 1. All right. I love these problems, and you will 100% see something where you need the following setup on the AP exam. If I integrate something, let's call it velocity, that would result in position, okay? But if I want bounds, let's say from, I don't know, 7 to 10, isn't that the upper bound in position minus the lower bound in position? It is. It is, kids. And that's what we're going to do right here. So how do I identify that? Well, let's go purple for P. Okay, start with particle P. I know that if I integrate my velocity of my particle P with respect to time, you must put dt. If you do not put that dummy variable, they can mark that wrong. All right, that's going to give me some sort of position of particle P, okay? But here's the thing. They say at time 0, the position is 5. So I have one of my bounds here, P of 0. They want us to know, well, at time 1. So I'm really going from 0 to 1. So I'm going to say the position at 1 minus my position of my particle at 0. And this becomes, I'm going to erase this side here, this becomes a really simple formula, especially if you have the calculator. All right? We know that P of 0 is 5. It tells us that. Times 0 is 5. So I know I'm going to subtract 5 from here. I am solving for this. This is the unknown. Okay? So this is what I'm going to solve for. All I have to do is put this part in the calculator and put that value right there. So let's open up our calculator, and let's scroll up so I can see what my equation is. And it is in the top right of the board. Turn this on, and you better be in radian mode because we have trigonometry. You see the blinking cursor? Better be on radian and not degree. Okay? Math 9 is where I go on my calculator from time 0 to time 1. Of course, I'm using x instead of t, but it's really the sine, parenthesis, of x raised to the 1.5. And don't forget our dummy variable x. That right there is going to be what's going to be on the left side of my equation. We'll round it 3 decimal places. So that will become a 1.371. 0.371. All I need to do is literally add 5 to both sides. I mean, that's how easy it is. Just add 5 to both sides. So my position of particle P at time 1 is 5.371. But we need to do this for both particle P and particle Q, which, big deal. We're bosses. We can do anything we want. So we're going to go ahead and do that. We'll start this in gray. And the same rule applies. Okay, they give me, at time 0, the position is 10 for particle Q. All right? So I know if I integrate particle Q, time 0 to time 1 again, okay, the velocity with respect to time, that's going to give me the position of particle Q. But now I have bounds from 1 minus the position particle Q at 0. They tell me the position at 0 is 10. So it's really the same thing. I'm just going to add up adding 10 to both sides. Put this right in a calculator. All right. Now, Q, the equation for Q is right here. And of course, I'm going to use an X instead of a T. So what do I do? This. We'll swap these out a little bit. This will come on this side because it's easier to see my equation. I am going to go math 9 again from 0 to 1. And this time my equation is going to be X minus 1.8, close that parenthesis, times 1.25 raised to my variable X dx. Booyah. Negative 1.43, and this will round up to a 6. Oh, I like the highlighter on the calculator. Right? Negative 1.436. Okay. Negative 1.436. And I'm going to add 10 to both sides. Boom. So my position of particle Q at time 1 is, oh my God, 8.564. And there we go. But the whole premise behind this problem, and I guarantee you will see it on a final, is when you integrate something, okay, if you integrate the derivative, you go back to the original equation. If this is velocity, this is position. If you have bounds, if they give you one of the bounds for these, A, and they ask you to find the bound for it in the other one, wow, that was strange, it changed. It's just a basic rule of integration. You will see that, absolutely, on an exam. 2B, are particles P and Q moving toward each other or away from each other at time equals 1? All right. Well, I like what they're doing here. We're going to use our answers from part A. All right. And, we're going to need to use our equations in order to determine direction of a particle. We need to look at velocity. Okay. If velocity is positive, that means it's moving to the right. If velocity is negative, that means it's moving to the left. Okay, so let's take a look at these right now. We were given the velocity of both of these. The velocity of particle P is this. Okay, the velocity of particle Q is this. So if they want to know that at time 1, I'm just going to throw a 1 in for those variables. All right, so let's go ahead and do just that. We'll go green for P, so the velocity at particle P at 1 is the sine of 1 raised to 1.5. All right, and I'm just going to put that in a calculator. Why would I do anything else? Okay, clear this out. Oh, you terrible, terrible calculator. So I'm going to say the sine of 1 raised to 1.5. It's 0.841. Okay, 0.841. Since this is greater than 0, it's moving to the right. All right. Well, let's do the velocity of particle Q at time 1. Again, I'm going to throw 1 in for my t's. So we've got 1 minus 1.8 times 1.25 raised to the power of 1. Again, I'm going to use my handy-dandy calculator because I can. And I'm going to say in parentheses 1 minus 1.8 times 1.25 raised to the 1. That is negative 1. Interesting. That equals negative 1. And that is less than 0, or it's negative, so that's moving to the left. Now, what we need to see is where are the particles at time 1. Just because particle P is moving to the right and particle Q is moving to the left, are they moving toward each other or are they moving away from each other? And what I mean is the following. If here's a little line here, okay? And I'm going to do particle P will be in green. Particle P, it's P. Particle Q will be in purple. Okay. In this situation, if P is moving to the right and Q is moving to the left, they're moving toward each other. But what happens if P is on this side and Q is on this side? Now if particle P is moving to the right and Q is moving to the left, they're moving away from each other. So it depends where they are before time 1. Maybe at time 0. Maybe if we look at the position for time 1, correct? We just did in part A, we found the positions of these particles at time 1. Okay, if I go back here, the position of particle P at time 1 was at 5.3, we'll call it. At Q, it's at 8.5. All right? So P is at 5.3. Let's say right here, this will be 5.3. This is where P currently is, right there at 5.3. And Q, well, Q is at 8.5, we'll call it. Right here is 8.5. Okay, so Q is already at 1 second to the right of where P is. So if P moves to the right and Q moves to the left, they are moving toward each other. So explain your reasoning. Here we go. A lot of writing. Since P is at 5.3 at time equals 1 and, well, that looks like a W. Moving right while Q is at 8.5 at time equals 1 and moving left, scroll down, P and Q are moving toward each other. There you go. Whew, that was more to explain and write than it was to actually do the math. But we're past A, we're past B, we're halfway done. I mean, guys, 2C. I mean, this whole problem has almost been a layup. If you understand for part A, integration Okay, integration is takes you from velocity to position, from the upper bound to lower bound. I mean, the rest of this has been cake, and part C is also cake. And I think I mentioned in problem for your response question 1, I love chocolate cake. And that's why I love these problems. Part C says, find the acceleration of particle Q at time 1. Is the speed of particle Q increasing or decreasing at time 1? Explain your reasoning. I am laughing because this is you are good at calculus, and this should be easy. In order to get acceleration, I need to find the derivative of velocity. They give me the derivative of velocity. Not only do they give me that, okay, I want to find the acceleration at time 1, so I'm going to find the derivative of velocity at time 1. Not only do they give me that, this is a problem you get to use the calculator on. My goodness, the calculator will do this whole thing for you. So I need to find, clear that out, the derivative of that circled equation in gray. I'm going to go math 8 d over dx. In my parentheses, I enter the equation I want to take the derivative of. So it's x minus 1.8 times 1.25 raised to the x. We're using x's instead of t's. And at what value of x do I want that derivative? When x is 1, when time is 1. That is 1.02. We will round this up to a 7. All right? 1.027. This is the acceleration at time 1. All right. There you go. Doesn't ask for a label or anything. Is the speed of the particle increasing or decreasing? My God, children, if you are a student in my class, or if you have ever listened to any of my videos, this is a scalar. I think it's called scalar, and I think that's how it's spelled. That's an R, by the way. Relationship. Okay, velocity and acceleration. I say it's a lot like multiplication. If the signs are the same in multiplication, you end up with a positive product, right? If the signs are different in multiplication, you end up with a negative product. This is telling me whether it is speeding up or slowing down. Here it's speeding up because it's plus, and here it is slowing down because it's minus. So I need to look at both acceleration and velocity at time 1. We already have our acceleration at time 1. It is positive, okay? If it's positive, acceleration is positive, acceleration is positive. I don't want a negative acceleration. I now need to look at velocity. For part B, we just figured the velocity of particle Q at time 1, okay? The velocity of particle Q at time 1, it's -1, okay? So we could do a Q here. The velocity of Q at time 1 is -1. Oh, look, so negative. We have a negative velocity and a positive acceleration. So it is slowing down. And I'm going to answer that, and you need to be specific because they get really, really picky. So particle Q is slowing down. Be specific. At time equals 1, since. Don't just say velocity is negative and acceleration is positive. Say the velocity at time 1 is negative, but I say less than 0 because it's less writing. And the acceleration of Q, I guess I should put a Q there, at time 1 is greater than 0, which is positive. That is it. But be specific, okay? Well, first of all, answer the question. At this time, why? Because the velocity at this time is negative, and the acceleration at this time is positive, okay? Be specific. Easy layup, cake, kids. It's cake. Put this back down here. Give it a little pause. Guys, I can't tell you how much of a layup problem 2 has been. It's been a pleasure to go over this with you. 2D, find the total distance traveled by particle P. Well, if I know anything, if I remember anything when we first started learning about integrals, distance is the area under the curve of velocity. This is velocity, but they want particle P, so let's not mess that up. Here's my velocity for particle P. This is the equation right here. The area under the curve for velocity is position, okay? But area under the curve is also better known as an integration. So if I integrate the velocity, okay, that gives me the area under the curve from 0 to pi. So from 0 to pi. Where is the one place you might get tripped up? If I just do a normal integral, that is considered displacement. What do I mean? Oh, that'd be nice if that was, I'll just change that here. What a regular integral is just displacement. If I have a graph that goes like this, like here, everything above the x-axis is considered positive, this area, and everything below the x-axis is considered negative. That's displacement. If I want total distance, it doesn't matter which direction I'm moving. I want to count every step. Like if I'm walking and I walk to the right, this is where I start. If I walk to the right 5 steps, then I walk to the left 3 steps, that means my displacement is 2, where I am compared to where I started. I started here, I'm 2 places. That's what integration is. Consider this 5 to the right, because there's just 3 to the left. That's why this is negative. 5 minus 3. That gives me my 2. That is what I'm doing right now. But the minute I saw this, total distance, everything in my graph should now be considered positive. This should be a positive 5, and this I want to be a positive 3. So consider my walking thing here. I took 5 steps to the right and 3 steps back. How many total steps did I take? 8. So displacement versus total difference, there are differences. For total distance, it doesn't matter where I am, above or below, they should all be positive. So how do I do that with an integral? All I have to do is use the absolute value bars on my equation, and that will make everything positive. If you do not, sometimes if you don't do the absolute value bars, you might get lucky, meaning, what if my graph is just above the x-axis? It's going to be positive no matter what I do because it's above the x-axis. But if it's not, then your answer will come out wrong. So all we're going to do is put my velocity for P in the integral from 0 to pi. All right, let's get started. Let's move this over here. And let's open this up. Boom. Over here, get rid of this, turn this on. Okay, get rid of those again. Delete, turn this on. Clear this, and we're going to math number 9. That's my integral from 0 to pi. And I'm going to put the sign in parentheses of x raised to the 1.5. Pop out of there, dx, and hit enter. And it's still thinking. 0.51, we'll raise that 4 up to a 5 because the number after it's 5 or bigger. 0.515. I'm going to take this. Wait a second. Wait a second. Find the total distance from 0 to pi. That doesn't seem right. And those of you guys that might have just heard me talk about, okay, these absolute value bars, that didn't feel right to me. Look what I'm missing here. My absolute value bars. Oh, Visca, you're devilish. All right, so what I need to do is the same thing. Math 9, from 0 to pi. Look, man, that's nuts. The absolute value is if I hit the math button and I move over to number, the absolute value is right there. Now I can put in the sign, woo, of x raised to the 1.5, close that out, be done with it, of x, hit enter, and let it spin the spinning circle of death. It's going, it's going. 1.931. There it is. 1.931. If you go, and those are ones, those are not absolute value bars. All right. Easy. Let's not make mistakes and go fast. I will see you for problem 3. Ta-ta.
Don't forget to subscribe and ring that bell.